At first glance, this looks like a drone flying a planned route. What you don't see is how many assumptions had to fail before it could fly this reliably. The goal was to study agriculture microclimates, small but important changes in temperature and humidity that get missed when farmers treat the entire farm as one uniform space. To do that, the drone needed to know where it was, stay stable in the air, and send data back reliably. On paper, that sounded straightforward. In practice, each part broke, one after the other. And the first thing to break was the navigation. The drone kept drifting off its planned path, not enough to crash, but enough to make the data useless. At first, I thought the drone just needed better tuning. But when I logged its position over time, I noticed something else. The drift lined up with weak GPS signals, not unstable flight. That was the first real turning point. The problem wasn't how the drone flew, how it knew where it was. So I replaced the GPS module with one that could lock satellites faster and update its position more reliably. Immediately, the flight path became more predictable instead of random. But fixing that raised a new problem. Now that the drone was flying better, I needed to understand why each flight worked or didn't. That meant relying on live data coming back from the drone. Mid flight, the signal just dropped. When that happened, I couldn't see the position, sensor readings, or anything else. At that point, I wasn't improving the system, I was just guessing. I traced the issue to an unreliable radio link and replaced the telemetry system. From then on, every flight gave me usable data. But data alone doesn't help if the drone can't respond properly. I was using a low-cost flight controller. It worked, but most of the automatic features were missing. That meant no auto-calibration, limited safety features, and a lot of manual setup. I had to calibrate the motors myself. Okay, so after hours and sheer hours of work on software, okay, I have finally gotten the motors to spin, okay? Look at this, look at this. Okay, so this took so long, okay? It took so long, but holy is it done. Once the drone itself was stable, the focus shifted. Now the question was whether the data meant anything. I tested different temperatures and humidity sensors, knowing that noisy data would ruin the whole project. Adding a camera also introduced more power issues. Motors pull a lot of current, and sudden spikes can crash the electronics. So I used a regulated power supply called a UBEC to give the Raspberry Pi and sensors clean and stable power. At this point, the drone wasn't just flying, it was actually collecting reliable information. All of the data the drone collected needed to make sense. So I built a simple interface to visualize what the drone was collecting. Each flight gets mapped automatically with temperature and humidity, overlaid along with the drone path. Instead of raw numbers, you can see the hotspots, areas where conditions differ from the rest of the field. Each fix removed a different source of uncertainty. The drone knew where it was, data stayed connected, sensor readings lined up with positions, and when something went wrong, I could actually tell why. This project wasn't about building a drone. It was about watching assumptions fail and fixing them one by one until they stopped failing.